Hey, welcome back everyone. In chapter 6, we're going to now discuss continuous probability distributions. But first, let's review the learning outcomes for the chapter. So in this video, we're going to focus on the first 3 learning outcomes of the chapter, which covers the normal distribution and how to use it to determine the probability of specific events. Then in the next video, we're going to learn about the exponential probability distribution. So let's get started. So the first topic will be the normal distribution. The normal distribution is a bell-shaped distribution with the following properties. First, it's symmetrical in that each side is a mirror image of the other. It is unimodal, meaning it only has one mode. The mean, median, and mode are all equal, and the amount of variation in the random variable determines the height and spread of the curve or the distribution. And our distribution is asymptotic in that it does not ever reach the x-axis. So our normal distribution can have different shapes depending on the mean and the standard deviation. So by changing the mean, we shift our distribution to the left or to the right. And by changing our standard deviation, it increases or decreases the spread or the width of the curve. If you recall in chapter 3, we learned about the empirical rule. So 68.26% of our data falls within one standard deviation of the mean, and 95.44% of our data is within 2 standard deviations of the mean. And almost all of our data, or 99.74%, falls within 3 standard deviations of the mean. So you can see when working with the normal distribution, there's only a really small chance an observation will fall outside of 3 standard deviations from the mean. So these would be considered extreme outliers. So here is a normal probability distribution function formula. So in this video, we're going to focus on using Excel to find our probabilities, but I really wanted to at least show you the details of the formula so you could review it on your own. So with our normal probabilities, because x is a continuous random variable, and if you recall in chapter 5, we were working with discrete random variables, which are numbers that you can count. In chapter 6, we're working with continuous random variables in that you can't count them because they include all values even down to the decimal. So that means the probability of any particular x is approximately equal to 0, and it's not very useful for us to try to find an exact probability for a given x value. So instead, when we're working with continuous random variables, we're looking for the probability for a range of values between x sub 1 and x sub 2. We could also be interested in finding the probability of less than or greater than a specific value. So for instance here, I might be looking for the probability of something occurring between 2 values, and so I want to find the probability for a number lying in the area shaded in yellow here. So let's discuss the standard normal distribution next. So for any normal distribution, we can scale it into the standard normal distribution. This is where we can convert our x values into z values. You learn how to do this in chapter 3. So by converting our x value into a z value, we can then compare different sets of data consistently. So recall our formula is where we take our x value and subtract our mean, and then we divide it by our standard deviation. And so once we convert our x's into z values, note that on the right side, our z values are positive. This is because our x values are higher than the mean. So this results in a positive z value. Vice versa, on the left side, our z values are negative because they fall below the mean. Essentially what we're doing here is standardizing the data. So the mean value is 0, and any x value that we're interested in is converted to a z value. And the z value represents how many standard deviations it is from the mean. Let's go ahead and review an example of calculating the z value as a refresher. Here is our x distributed normally with a mean of 100 and our standard deviation of 50. So what is the z value if our x is 250? So here is the z formula again. So we're going to plug in x of 250 minus 100 for our mean, and then we're going to divide it by our standard deviation of 50, and we get 3. So in other words, this means that 250 is 3 increments of 50 units above the mean of 100. Recall in chapter 3 that you learned how to use Excel to standardize an x value into a z value for the normal distribution. So now using Excel, The first step that we must do is to find our mean and standard deviation. These will likely be given to you in the problem, but if it's not, and you're given a data set, you know how to use Excel to find our mean and standard deviation. The next step is to make sure we understand what the event of interest is that we're trying to solve for. Then we'll be using Excel, and in particular the norm.dist function, to find the cumulative probability. And then in step 4, we're going to find the desired probability that we identified in step 2, and using the knowledge that the total probability under our distribution is equal to 1. If you recall in chapter 4, we learned that one of our probability rules says that all of the probabilities added up are equal to 1. Now, our Excel function for the normal distribution gives us the cumulative probability from left to right. So adds up all of the probabilities starting on the left side up until whatever number you're interested on the right side. So you could write the formula manually in the formula bar in Excel, or you could use the formula builder by using the Formulas tab and clicking on the Insert function, selecting the statistical category, and then choosing norm.dist. Then the menu will appear, and for each component for our function, it will remind you what you need to put in. So you will input the x value, the mean, the standard deviation, and then for cumulative, we're going to type in true. Then you'll hit OK, and you'll see the result. Over the next couple of slides, we're going to walk through some examples. So suppose x is normally distributed with a mean of 8 and a standard deviation of 5. We want to know the probability that x is less than or equal to 8.6. That means I want to know the chance that x is going to be any value of 8.6 or below, which is highlighted here in yellow. So down here at the bottom, we have the formula to calculate the z value for our x value of 8.6. So we can rewrite that probability that x is less than or equal to 8.6 is the same as saying the probability of z is less than or equal to 0.12. So knowing that Excel gives us the cumulative probabilities reading from left to right up to 8.6, we're looking for the area with the green arrow here. So we would type in equals norm.dist, 8.6 is the x value, 8 is the mean, 5 is the standard deviation, and then we'll type in true because true will give us all of the probabilities from left to right, and we get 0.5478. This represents the probability, or 54.78%, of our data that falls in the yellow shaded section here under our normal curve. And it's a likelihood of getting a value less than or equal to 8.6. So here's another example. Suppose that x is normally distributed with a mean of 8 and a standard deviation 5. So that is the same as the prior problem, but what we're changing now is the event of interest. So here, what we want to find the probability that x is greater than or equal to 7.5. So 7.5 is on the right side of the mean, and so now we're interested in all the possible values that are greater than or equal to 7.5, shown by the green arrow here. Again, if you want to convert our x value into z value by hand, we have the formula down here at the bottom. So plug in 7.5 for x and subtract the mean of 8 and divide by 5, and we get a negative 0.10. We can rewrite our event of interest as a probability that z is greater than or equal to negative 0.10. So here we'll be using Excel again to do the calculations for us, but we know that it turns a cumulative probability from left to right. So it's going to tell us about the area from the left to 7.5, shown here by the blue arrow. However, that's not the area that we're interested in. We're interested in the area to the right. So we'll have to apply the complement rule that we learned about in chapter 4. So first, let's find the area here using equals norm.dist, the x value of 7.5, the mean of 8, standard deviation of 5, and then type in true, and we get 0.4602. That'll give us the probability for that area to the left of the yellow shaded area. So I'm going to take 1 minus 0.4602, and we get 0.5398. Now that represents the region that we're interested in, and it's a probability that x is greater than or equal to 7.5, or a 53.98% chance. Let's do one last example. Suppose x is normally distributed with a mean of 8 and a standard deviation of 5 still, but now we're interested in the probability between two values, where x is greater than or equal to 7.5 and less than or equal to 8.6. This is the yellow area that I've also notated with the green arrow. Again, we can convert our x values into z values and restate our probability that z is somewhere between negative 0.1 and 0.12. We won't review the z calculations again, but we have them shown here down at the bottom. So the blue areas show the regions for the normal distribution that we'll be doing our calculations for each x values of 7.5 and 8.6. We'll be doing each of these calculations separately, and then we're going to use the numbers together to calculate for the probability of the region that we're interested in. So first, we'll do the calculation for the region below 7.5. So we'll type in norm.dist with 7.5 for our x, 8 for the mean, 5 for the standard deviation, and then type in true, and we get 0.4602. Then we must do the same thing for our x value of 8.6. We'll type in equals norm.dist, the x value of 8.6, the mean of 8, standard deviation of 5, and type in true as well. And we get 0.5478. So now that we've calculated the two areas, we can use these two numbers to calculate the region that we're interested in. So we're going to take 0.5478, and then we're going to subtract 0.4602, and we get 0.0876. So therefore, the probability that our x is somewhere between 7.5 and 8.6 is relatively small at 8.76%. Let's go ahead and wrap this up with another practice problem. So assume a population is normally distributed with a mean of 100 and a standard deviation of 20. We're going to work with three different scenarios. So in part A, we're looking for the probability for a value greater than 130. Then in part B, we're looking for the probability that the value is less than 90. And then in part C, we're looking for between 90 and 130. So since the steps here are like the previous example, we're going to set all these up on one slide. So in part A, we have the probability that x is greater than 130. So here's our normal curve, and we're looking for the probability for the yellow region. So like before, I'll use green arrows to denote the section from left to right that we're interested in. But as we know, the normal distribution gives us a probability from left to right, so we'll denote this region by the blue arrow. So plugging in our x value of 130, our mean of 100, our standard deviation of 20, and true for cumulative, this returns the probability for the area to the left of what we're interested in. We'll use the complement rule and take 1 minus 0.9332, and we get 0.0668. Let's look at the next one. So in part B, we're looking for the probability that x is less than 90. Since we're doing less than some value, we can actually use the output of the norm.dist function directly. So we are looking for the probability for the region from the left to right as shown by the green arrow. So plugging in our x value of 90, our mean of 100, our standard deviation of 20, and true for cumulative, and we get 0.3085. So in the last one here, in part C, now we're interested in finding the probability that x is between 90 and 130. So here's our normal curve, and we are interested in the yellow area denoted by the green arrow. Now, we already did both calculations that we need to find the probability for both areas denoted by the blue arrows. In part A, we first found the probability of x being less than or equal to 130, and then took the complement of that number. But here, we'll be using the probability from the function that represented the area from left to right, or 0.9932. Next, we'll use the probability that we found in part 2. Next, we'll use the probability we found in part B and subtract 0.3085 from 0.9332, and we get 0.6247 for the probability of x being between 90 and 130. Well, everyone, that wraps up this video on an introduction to continuous probability distributions and the normal distribution. In our next video, we'll learn about the exponential probability distribution.